Well, good evening, everyone, and welcome to the Brian Crombie Radio Hour on Saga 960. In my continuing endeavor to bring you some cutting-edge science and some inspirational people, I want to introduce you tonight to Professor Molly Shoichet. Is that right? Shoichet. I apologize. Molly Shoichet, who is a professor of chemical engineering and applied chemistry at the University of Toronto, and she's a Canada Research Chair in Tissue Engineering, and more importantly right now is that she's a recipient of Canada's top $1 million Science Prize and Gold Award. And the professor says that the good thing about it is the $1 million all going to go to the science. So that's great. So Professor, tell us, what did you earn the Science Prize for?
So we've been really excited about working at the intersection of engineering, chemistry, and biology. And what we've designed over the years are a series of hydrogels. So these are just water-swollen materials. So you might think of Jell-O, or you might think of the hydrogel in the diapers that you might use on your child when they were a baby. Those are all hydrogels. We did not invent those. What we did is we invented new materials that we could use to understand and answer questions in biology and solve problems in medicine. And then I can go into more detail if you want.
Please do. So these hydrogels, what is it that they do?
So we've invented a whole series of different hydrogels, and we've used some to model cancer. So some cancers like brain cancer or lung cancers are highly invasive. And so for the first time now, we can model that invasive behavior in these hydrogels. And so you might say, who cares? And the reason why that's important is when we try to discover new drugs that will be useful to treat cancer, we want to, of course, come up with drugs or therapeutics that will kill the cancer cells, but also ones that will stop their invasion if they're highly invasive. And so now, because we have this really cool tool that will allow us to model invasion in the lab, we can now screen for drugs and hopefully come up with better drugs for the treatment of these very devastating cancers. And so that's half of what we do. And then there's a whole other half, but I'm happy to answer questions on this.
Okay, so that is what the prize was for these hydrogels, and these hydrogels that somehow teach you about how the aggressive cancer cells work?
Yeah, exactly. So the Natural Sciences and Engineering Research Council of Canada, or NSERC, funds fundamental research in science and engineering. And our work we've invented all these new materials that now enable us to do things that we've never been able to do before. So some of our research is applied to cancer, and the other side of our research is applied to a field called regenerative medicine. And so I think a lot of people have heard about stem cells and how stem cells have the capacity to help us regenerate tissues. And so we've also designed hydrogels for something completely different from cancer, and that would be to promote tissue regeneration, for example, in the brain after stroke, or at the back of the eye in the retina in diseases related to blindness.
Fantastic. So sorry, you have invented the stem cells, or you've invented a way to have these stem cells convert into tissue regeneration?
Yeah, so we haven't invented the stem cells, but one of the fundamental challenges that we face in stem cell regeneration is that most, if not all, of the stem cells die after they've been transplanted. And so what we've done is we've designed ways to transplant those stem cells so that more of them survive. And so in the context of the nervous system, which is the system that we study, you can imagine if you throw in a bunch of cells and they don't survive, or they don't integrate into the neural circuitry of the brain or the eye, then they're not going to do very much. An analogy that I like to use is you've got a cable of hundreds of thousands of wires that you've now severed. And if you just throw in a bunch of wires, probably not going to restore that electrical conductivity. And so the same thing is true in the tissues and in the nervous system. If we just throw in a bunch of cells and they don't integrate into the existing neural circuitry, then you're not going to, restore brain function, or you're not going to restore vision. And so what we've done is worked very closely with the biologists, with the clinicians, to invent these materials that enhance the survival of those cells when they're transplanted, so that more of them survive and then more of them integrate into that neural circuitry.
Fascinating. And this earns you $1 million, and you get to spend $1 million on the research.
Yeah. So what's so exciting is, any good research question will open up so many more unanswered questions. And so while we've made enormous progress in the research we've done, at the same time, we've realized that there's so much more that we need to do. And so having this $1 million over the next 5 years focused on research really gives us the opportunity to advance those fundamental discoveries further. And then, our ultimate goal is to make a difference in human health. And so we have translated some of our discoveries into startup companies, that allow us to go from that fundamental discovery ultimately to make a difference for people.
We're chatting tonight about stem cells and polymers and hydrogels, and it's going to be a fascinating conversation. We're going to take a break to just a minute for some messages and come back more with the professor in just a minute. Stay with us. Welcome back to the Brian Crombie Radio Hour. We're chatting tonight with Professor Molly Shoichet, who is a Canadian science professor at the University of Toronto. She specializes in chemistry, biomaterials, and biomedical engineering. She was Ontario's first chief scientist. She's a biomedical engineer known for her work in tissue engineering, and is the only person to be a fellow of 3 different national academies in Canada. Interesting enough, she won the Order of Canada in 2018. She won something called the Killam Prize for Engineering in 2017. I want to ask her about the L'Oreal UNESCO for Women in Science prize that she won in 2015. She's won the Queen's Diamond Jubilee Award in 2013, which I'm also a recipient of, by the way. And she won the Order of Ontario in 2011. So she's got quite the impressive background. She got her PhD in the United States at the Massachusetts Institute of Technology. University of Massachusetts Amherst, with a PhD in polymer science and engineering. And she's recently won $1 million prize to do some further studies. Professor, I had on a gentleman from the University of Alberta that was doing work in diabetes. And what he did is he said that the problem with stem cells is if they're not your own stem cells, and the problem with transplant is if it's not your own material, then the body rejects it. And so what he was doing is he was taking stem cells from the host, the person that was going to be put back in. What are you doing with stem cells?
Right. So there are cells that you can derive from humans that are called induced pluripotent stem cells. So these cells are taken from adult tissue and basically turned backwards into stem cells and then reprogrammed into the different cell types of our body.
And there's some fancy Japanese name for what this reverse engineering is?
Well, I don't know that it's a fancy Japanese name, but one of the Nobel Prize winner in 2006 was a Japanese scientist who discovered the 4 factors that were required to turn adult cells back into stem cells.
And stem cells are what? Are cells sort of at the time of conception, correct?
Yeah, so stem cells, depending on where they are, have the capacity. So if they're the pluripotent, so potent is just power and pluri is many, the pluripotent stem cells have the capacity to become, like the embryonic stem cells, have the capacity to become any cell type in the body. whereas the adult stem cells have the capacity to become any cell type within that adult tissue. So for example, adult brain stem cells have the capacity to become any cell type in the brain, but they don't have the capacity to become any cell type in the body.
Okay, so are you using this effectively the same process, or are you using stem cells from somebody else?
Yeah, so right now we're working with the pluripotent stem cells. And so there are a series of cell lines that actually the US government had said that researchers can look at, and those are very well studied cell lines. And then your researcher from Alberta is right. We have to really be careful about immune rejection of those cells once they become differentiated. So there's a number of different strategies that people all around the world are investigating, either to use your own cell type. So you could imagine taking a bit of your skin, your own skin, and turning those backwards into those pluripotent stem cells, and then forwards into the cell type that you want to transplant. Or you can work with one of these defined cell populations for transplantation.
Okay, and so you are taking these stem cells and you're doing some regenerative medicine. Tell us what regenerative medicine is. Are you recreating brains or something?
Yeah, so that's really cool. So, you might think, we always think of the brain as kind of like the final frontier in medicine, just because it's so complicated. And of course, the brain controls everything. It's the control center of our bodies, whether it's feeling, like understanding the senses that we feel, or controlling the movement of our bodies. And so in stroke, for example, which is a traumatic injury in the brain, when you've depleted the oxygen supply, we lose, some people lose motor function, some people, depending on how severe the stroke is. And so we've been collaborating with Cindy Morsed's lab at the University of Toronto to come up with strategies to enhance basically brain repair. So actually trying to regenerate brain tissue. So what's so exciting about the brain is that probably, Brian, when you and I went to school, we learned that, however many brain cells you have in your brain, that's what you got.
And if you drink too much, you're going to lose them all, my mom said.
And if you drink too much, you're going to lose them all. And yeah, that's what my mom said. And that's actually what I told my kids too. But it's not actually true, because our brains do have the capacity to regenerate. And so that was a discovery in the early 1990s, that our brains, actually the adult brain, has stem cells in it. And when someone has a stroke, those stem cells are activated, but not sufficiently to regenerate the tissue. And so in collaboration with Cindy Morsed's lab, we've been looking at different ways of stimulating those resident stem cells and getting those cells to regenerate brain tissue. So that's really exciting. And that's really thinking about, okay, so what proteins, what therapeutics can we deliver directly to the brain to stimulate those? And so my lab, being from an engineering perspective, we've been thinking, okay, how do we deliver these factors? How do we get them to the brain tissue? How do we get them to diffuse through the brain tissue? So these are all engineering concepts that we can now apply to biology and medicine.
Now, if someone's got a stroke, that obviously is something that needs to be repaired. But what about dementia or Alzheimer's? Is that something where you think you could actually regenerate stem cell growth to repair brains that have been harmed by dementia or Alzheimer's?
Yeah, ideally. So we're not working specifically in those areas. It's as we get older and older, our capacity to regenerate our tissues is harder and harder. And that's partially based on the environment in which these cells reside. So it's not that the stem cells themselves don't have the capacity to regenerate, but they have to still have a good environment to regenerate into, which is our brain tissue. And so a nice analogy is an agricultural one, where you're planting seeds, and if you're planting seeds in soil that's not sufficiently nourished for those seeds to take and to grow, then they probably won't. And so, what we're looking at is trying to not only stimulate those stem cells so that they can grow and regenerate, but at the same time, enhancing that environment in which they need to grow to give them a better chance of growing and reconnecting and regenerating that tissue.
And that better environment is these hydrogels?
Yeah, it's the hydrogels, but also it's imbibing the hydrogels with proteins, releasing those therapeutic molecules that will, both change the microenvironment in which the cells are growing to make it richer, and then also giving those cells the opportunity to survive a little bit longer.
So you're repairing brains or regenerating brains, brain cells, not by, a new pharmaceutical or something like that, but by just assisting the existing stem cells in the brain to grow and repair in its own natural way, but in a better environment.
Yeah. And you bring up a really good point, because the question is, well, what therapy should you be delivering? We've actually in my lab developed all these really interesting strategies to deliver therapeutic proteins to the brain, but we still need to figure out what are the best ones to deliver and how long do we need to deliver them. So that's why I said, at the very beginning, every time we make an advancement, we open up so many more questions, which leads to greater discovery. And so I just don't want people to walk away thinking that we've got all of these answers, because there's still so much more that we need to learn.
Understood. So these hydrogels, this is a material that you would use to make a pill out of, or a capsule, or a what?
Yeah, so they're so in our brain research, for example, you can imagine like a little depot, or I think of it as a little like drug-infused Band-Aid, or a little patch that you'd put not on your skull, but directly on your brain. And then the molecules will diffuse into the brain to stimulate the endogenous stem cells. So it's injectable. So, imagine, you can imagine like a two-part epoxy where, you have a liquid and then they mix together and they form a little solid. Although epoxy is hard and brittle, and these are soft and malleable. So they match, our skulls are obviously quite hard because it's bone, but underneath that bone is our brains, which are quite soft and squishy. And so is our material. So it matches the mechanical properties.
So what are you drilling a hole in the brain to get this epoxy inside of it?
Yeah.
Sorry, drilling a hole in the skull, not the brain.
Yeah. If someone has a stroke, if you were trying to decompress the brain, or if you have a hemorrhage and those are quite invasive surgeries. So you wouldn't have to do more. But also, let me just say, we're not working on humans yet. So there's still a long way before we get there. We've also looked at delivering stem cells to the back of the eye in diseases of blindness. And there's a less invasive way to get to the back of the eye, but still you have to get to the back of the eye, because that's where the retina is. And when you see, light travels through your entire eye all the way to the back to the retina, and those cells capture light and send signals to the brain. So we're also looking at strategies to replace the cells that are lost in blindness, and then using different materials to, again, inject those cells, replace the cells that are actually lost due to blindness, with the goal of restoring vision.
And the key to all this is this hydrogel formulation that is a better way of delivering whatever it is, the protein or the therapeutic that you want to deliver. Is that correct?
Yeah, so the hydrogel just allows us to do things that you can't do with the cells alone or the proteins alone. One is just localizing everything where it needs to be. And the other is having the cells delivered in such a way that they'll survive longer, and also integrate better.
So is part of the problem, and I read here that early in your career you studied the blood-brain barrier. Is part of this problem that getting across the blood-brain barrier is problematic, and so therefore the hydrogel helps you localize the therapeutic?
Yeah, so that's a really great question. So it turns out that the blood vessels in our brain protect our brains from toxins diffusing across those blood vessels into our brain tissue. So if there's, molecules, like most drugs we would take orally, right? Like we all have taken tablets orally, or you might have had an intravenous that's going through your blood vessels. And that's a way to deliver molecules to your body. But those blood vessels in our brain create a barrier. And so most molecules can't get across that barrier. And so that's why we've had to create this local delivery vehicle. And so another analogy is, imagine you're driving down a road and there's a roadblock. Okay, that's our blood-brain barrier. So you can try and go through that barrier, and there's some really cool technologies to do that. Or you can just try and go around the barrier. And so that's what we're doing with our drug delivery vehicles. And because we can't go across the blood-brain barrier, and we're only using those blood vessels to get into the brain tissue, we thought, well, why not just deliver drugs directly to the brain tissue? And so that's what we're doing
With this hydrogel.
Yeah.
It's interesting because you use analogies, metaphors repeatedly to try to explain things. You're very good at explaining scientific terms. I understand that in 2015, you co-founded Research to Reality, a showcase scientific research blog post and video series. Are you still doing that?
Yeah, so Research to Reality with the number 2 is really a passion. And it evolved out of my understanding that the public really wanted to know what was going on in research, because what excites me so much about research is this idea of inventing the future. But unless you're really going to spend a lot of time listening, you don't really have the opportunity to, the public doesn't really have the time or maybe the opportunity to really dive in. And so I co-founded Research to Reality with Mike McMillan, a feature film producer, where we could take advantage of the power of film to tell very short research stories and really just try and pique people's interest and engage them in what's going on in research and why do I care? Just those 2 simple questions. And if we can pique your interest, then maybe you want to dive down and learn a little bit more. And so we've created over about 250 videos of just amazing researchers across Canada, some international researchers as well. And it's just with that in mind, just to bring people into our world of discovery and, hopefully engage them in that process.
Excellent. And if people want to watch any of those videos, is there a website they can go to watch them?
Yeah, please do. Just research2reality.com. So just research 2 with the number 2 and reality. There's another Research to Reality with the TO, but that's not us.
That's not you. Okay. Well, I'm going to have to check it out because it sounds fascinating. I read a fascinating book by an Israeli professor, Yuval Noah Harari, called Homo Deus. And he writes that a lot of the things that it sounds like you're working on and other people are working on actually could advance some humans to such a extent that they almost become superhuman. But the risk is that if that's only available to the rich, that it's going to end up being comparable to Homo sapiens dominating the Neanderthals. What's the risk in some of the research you're doing? Is this going to be available to all, or are there going to be some people that have these hydrogels available to them and can repair their brains, and other people that won't be able to?
I think with all new technologies, initially they're very expensive. And as we learn more about the technologies, we can de-risk them and make them more available. So, at this point, we're still very early in our research. And I think that's a risk of all technology and all advances. Living in Canada, where we have universal health care, it's very important to us to make these affordable to everybody. And then obviously working, in the global society, the goal is to make this as available as possible to everybody in the world. But we're really so far from even getting this into human clinical trials. So that is our goal.
When do you think it could be in, you're in animals now, I take it?
Yeah, so we've worked in animal models of disease, in stroke and in blindness. And in our cancer work, we've really just worked in these model systems in the lab. And that's more for, the cancer work is really more for drug discovery. And the regenerative medicine work is really for tissue regeneration. So, as we've learned more about the science, we are, moving closer and closer to testing. First you have to test it in a small, we don't want to be testing this on people, right? We want to make sure that we've de-risked it so that when we get to the human clinical trials, that we have that we know as much as possible that it's going to be safe and it's going to be efficacious. So we have to, go from the small animal model to the larger animal model. And it just really takes a lot of money to get there. And so we would really, that's partially why we've started companies out of my lab, is because, through, the academic mission is really to advance knowledge, whereas the commercial mission is to bring products to market. Yeah, and commercialize it. And so, we'll take it as far as we can in the academy, and then either work with corporate partners that already exist, and that's what we'd love to do, actually. So we love working with the corporate world.
In addition to all of your other prizes, you did receive this L'Oreal UNESCO for Women in Science award. Is inspiring more females to be involved in science one of the things that you're interested in?
Yeah, 100%. I have to tell you, I grew up with girl power. So my mom was a very strong influence on me, just in terms of, seeking a profession and being independent. And I really loved science as a kid, and my mom and dad both encouraged me to do that. But I have to tell you, I'm married and I have 2 sons. And so I realized that having 2 sons, that I could be an influence not only for young women, but also young men. And I think really what we're trying to do is change society to be more inclusive generally, not just based on men and women, but also more broadly inclusive. And so, I hope to be a role model for young women to know that, they can pursue their dreams. And if they're excited in science, that they can have a career in science. But I think it's also really important to encourage young men, not just to go into science, but also to value, their female friends, their women friends, and value those careers. And that's something that, my husband has always not just supported my career, but valued my career as much as I have. And I think that's really important in society as well.
Well, it sounds to me like you're working on some pretty important stuff, whether it be brain cancer or strokes in the brain, or delivering medicine and proteins more targeted to the right places in the brain or other tissues in the body, such as the retina. So I look forward to the continuation of your research. And when you have more advances, please come back and tell us more about it. I've got to tell you, and you probably haven't been following it, but I had an interview with someone who was telling me about the impacts on the brain of COVID-19 and this long haul and the brain fog. And he said it was like a whole bunch of small little strokes. And so if that's going to be a coming issue, I wish you luck with the work that you're doing on repairing the brain with stem cells.
Thank you so much. And I really, really appreciate your interest in our research and your featuring it on your show. It's really a pleasure to be here with you.
Professor Molly Shoichet, correct?
You got it.
Who is a chemical engineering and applied chemistry professor at the University of Toronto, Canadian Research Chair on Tissue Engineering, and the recent recipient of Canada's top $1 million Science Prize and Gold Award. Thank you so much for joining us. And what was that website again? Reality to Science?
Research to the number 2 reality.
Research to reality. Got to check it out. Thank you so much for joining us. We're going to take a break and come back more with the Brian Crombie Show in just a minute. Stay with us.